Today, still session 4.3. We have 3 topics today. Topic 1, increasing, decreasing, concave up, concave down. We studied this topic in the last class, but today I want to show you one more example about this topic. Topic 2, more about critical points. Topic 3, using derivatives to determine local maximum values and local minimum values. Take a review first. Number 1, increasing, decreasing test. A curve is increasing on some interval if and only if derivative is positive everywhere on the interval. Here, we have an increasing curve. I place 2 open dots at the 2 ends of the curve because the interval that I am considering is an open interval. Open interval doesn't contain the 2 endpoints. Therefore, I place 2 open dots at the 2 ends of the curve. If you draw a tangent line between A and B, then the tangent line has positive slope. So therefore, a curve is increasing if and only if slope is positive. Similarly, a curve is decreasing then if and only if slope is negative. A decreasing curve, arbitrarily draw a tangent line, slope is negative. Review number 2, concavity test. A curve is concave up, then second derivative is positive everywhere. The reverse is also true. Second derivative positive, then the curve is concave up. A curve is concave down if and only if second derivative is negative. Keep this in mind. First derivative is about increasing, decreasing. Second derivative is about concave up, concave down. Keep this in mind. Review number 3. A point on a curve is a point of inflection if the curve changes concavity at the point. This curve changes from concave down to concave up at this point. So this point is a point of inflection. And this point is also a point of inflection because the curve changes from concave up to concave down. Changes concavity at this point. So this point is a point of inflection. Now, next, I present the topics today. Topic 1. One more example about increasing, decreasing, concave up and concave down. The graph of the derivative of a continuous function is shown here. Pay attention. This is the graph of the derivative f prime of x, not the graph of f of x. And also, all the questions are about function f of x, not about f prime of x. So all these questions not about this graph, this curve. This curve is the graph of f prime x. Okay, first question. On what intervals is the function f increasing, decreasing? By increasing, decreasing test, when derivative is positive, the graph of f is increasing. When derivative is negative, the graph of f is decreasing. This is the graph of derivative. From this diagram, we can see that between 0 and 2, the graph lies about x-axis. So between 0 and 2, this guy is positive. Derivative, this guy is positive over the interval 0 to 2. And similarly, 4 to 6, 8 to infinity, the curve lies above x-axis. So over these two intervals, this guy is positive. So therefore, the graph of x, the graph of f is increasing on these three intervals. Similarly, from 2 to 4, 6 to 8, the curve lies below x-axis. That means that over these two intervals, this guy is negative. Derivative is negative. So the function f is decreasing on these two intervals. This is A. Now B. At what values of x does the function f have a local minimum, a local maximum? To answer this question, I roughly sketch the graph of f. From A, function f is increasing on these three intervals and decreasing on these two intervals. So from 0 to 2, I draw an increasing curve. 2 to 4, decreasing curve, and then increasing, decreasing, and then increasing. Now, from this rough sketch of the function f, I can answer B. When x is 2, I can see that the curve has a highest point locally. And also at 6, the curve has a highest point. So at 2 and 6, the function f has local maximum. Here, function f has a local maximum at 2 and 6. At 4 and 8, the curve has a lowest point locally. So at 4 and 8, the function f has a local minimum. Function f has a local minimum at 4 and 8. Now, part C. On what intervals is the function f concave up and concave down? Okay, now go back to the graph of derivative. From 0 to 3, this curve is decreasing. So by increasing, decreasing test, derivative on this curve is negative because this curve is decreasing. So derivative on it is negative. In other words, derivative on this guy is negative between 0 and 3. Yeah. Derivative on this guy is negative. Derivative on this guy is second derivative on the function f. It is negative. over this interval. When second derivative is negative by concavity test, the function f is concave down over this interval. Similarly, from 3 to 6, the curve is increasing. So derivative on this curve is positive. Derivative on this curve is derivative on this guy. Derivative on this guy is second derivative on the function f, positive on the interval 3 to 6. So therefore, second derivative is positive. The function f is concave up on this interval. Similarly, from 6 to infinity, the curve is increasing. So derivative on this curve is positive. Derivative on this curve is derivative on this guy. Derivative on this guy is second derivative on f, positive. So over this interval, the function f is concave up. This is part C. Part D. State the x-coordinates of the points of inflection. Again, to answer this question, I roughly sketch the graph of f here. From C, function f is concave down on this interval 0 to 3. So 0 to 3, I draw a concave down curve. From 3 to 6, f is concave up. So I draw a concave up curve. And also 6 to infinity, f is concave up. So I draw a concave up curve. Now, based on this rough sketch, I can answer the question D. The x-coordinates of the point of inflection. The graph of f has only one point of inflection, this point, because the graph changes from concave down to concave up at this point. This is a point of inflection. This point is not a point of inflection because on the left, curve concave up, on the right, concave up. The graph doesn't change concavity at this point. So this point is not a point of inflection. Okay, now the answer to question D is the x-coordinate of the point of inflection is x is 3. Part E. Assuming function value at 0 is 0. That means that assuming the graph of f passes through the origin. Now sketch a graph of the function f. I suggest that mark down the information we got from A to D on xy plane. Mark down the information here. Say for example, from 0 to 2, from A, function f is increasing on 0 to 2. So 0 to 2, I mark down the information, okay, increasing. From 0 to 3, from part C here, function f is concave up on the interval 3 to 6. So, no, function f is concave down on the interval 0 to 3. So 0 to 3, concave down, I mark down the information. And similarly, mark down all other informations. Now, I'm ready to sketch the graph. Starting from the origin, because assume that the function passes through the origin. So I start from the origin and sketch the graph of the function f, piece by piece. The first piece, 0 to 2, the graph is increasing and concave down. So I draw a curve like this, concave down, increasing. Second piece, 2 to 3, the graph should be concave down, decreasing. So I draw a curve down and decreasing. 3 to 4, the graph is decreasing and concave up. So decreasing, concave up. Then increasing, concave up between 4 and 6. So increasing, concave up. Now, from 6 to 8, decreasing, concave up. So decreasing, concave up. And then 8 to infinity, increasing, concave up. So increasing, concave up. The graph of f at 6 has a corner. So derivative of f doesn't exist at 6. This is reflected by the graph of f prime of x. Say, at 6, there are 2 open dots. You cannot find solid dot at 6. That means that this guy has low value at 6. Derivative has low value. Derivative doesn't exist. So the graph of f has a corner at 6. Has a corner at 6. This is topic 1. Next, we study topic 2, the second topic. Second topic is more about critical points. Topic 2, more about a critical point. Recall that a point in the domain of a function is a critical point if derivative there is 0 or derivative there doesn't exist. Please note that a local extreme value can only appear at a critical point. Local extreme value cannot appear at other points, can only appear at a critical point. However, a critical point doesn't always correspond to a local extreme value. Below are some examples. About a critical point, there are 8 cases. Case 1, C is a critical point because derivative at C is 0. The tangent line at C is horizontal. In this case, the function has a local maximum. Case 2, C is a critical point because derivative at C is 0. In this case, the function has a local minimum. However, at case 3 and case 4, the function has neither maximum, local maximum, nor local minimum. This point is a critical point. Tangent line is horizontal, or derivative is 0. This is a critical point. Tangent line is horizontal, or derivative is 0. But in these 2 cases, the function f, has no maximum nor minimum at this point. Then case number 5 to number 8 correspond to a critical point where the graph has a corner. At the corner, derivative doesn't exist. Case 5, the function has a maximum. 6, function has a minimum. 7, the function has no maximum, no minimum. This point, locally, it is not the highest point, not the lowest point. This point is also locally, it is not the highest, not the lowest point. So the function has no maximum, no minimum at point C. So about this topic 2, the key point, let me repeat the key point. A local maximum value and a local minimum value can only appear at a critical point. However, at a critical point, the function may not have maximum, may not have minimum. Topic 3. Use derivatives to determine a local extreme value. In this topic, there are 2 theorems. Theorem 1, use first derivative to determine a local extreme value. Suppose C is a critical point of a function. If derivative changes sign from positive to negative at the point C, this case, on the left to the point C, derivative is positive. Therefore, on the left of the point C, the graph of the function is increasing. On the right to the point C, derivative is negative. Therefore, on the right to the point C, the graph of function f is decreasing. Therefore, the function has a local maximum value at the point C. So, you can use derivative to determine a local maximum value in this case. Case B, if derivative changes sign from negative to positive at the point C, this case, on the left to the point C, derivative negative, the graph of the function f is decreasing. On the right to the point C, the graph is increasing because derivative is positive. So at the point C, the function has, therefore, the function f has a local minimum value at the point C. Case C, if derivative doesn't change sign at the point C. For example, on the left side to the point C, derivative is positive. The graph of f is increasing on the left. Derivative doesn't change sign. So on the right, derivative is also positive. The graph continue to be increasing. So at the point C, the function has no local maximum, nor local minimum. Similarly, if derivative on the left to the point C is negative, on the right to the point C also negative, doesn't change sign, then the function, the graph of the function will be on the left decreasing, on the right decreasing. Again, in this case, the function has low maximum, low minimum at the point C. So this theorem says that you can use derivative to determine whether or not the function has an extreme value at a critical point C. Second theorem. You can also use second derivative to determine a local extreme value. Three cases. If derivative at the point C is 0, this case, at the point C, derivative is 0, tangent line is horizontal. If derivative at the point C is 0 and second derivative at the point C greater than 0, recall that second derivative is about concave up, concave down. Second derivative greater than 0, the graph of the function f is concave up. So these two conditions says that at the point C, tangent line is horizontal, and at the point C, the curve is concave up. Second derivative greater than 0 at the point C. So at the point C, the graph of f is concave up. Therefore, function f has a local minimum value at the point C, this case. Now B. If derivative is 0, at the point C, tangent line is horizontal. And second derivative at the point C, less than 0. Second derivative less than 0, graph of the function is concave down. So this condition says that at the point C, the graph of f concave down. Therefore, the function f has a local maximum at the point C, this case. C. If derivative at C is 0 and second derivative at C is 0, this case, the test is in conclusion. That means that the function may has a local maximum or a local minimum or neither or are possible. So this case, no conclusion can be made. Now in the following, let's see some examples about how to use these two texts to solve problems. Example 1, under this topic. Find all the local maxima and minima of this function. There are two solutions. In solution 1, I use this theorem first to answer the question. Then in solution 2, I use this theorem to answer the question. To find all the local extreme values of a function, we first find critical points because an extreme value can only appear at a critical point. So find all the critical points first. Compute derivative on the function. Derivative, this derivative has low denominator. So low critical points where derivative doesn't exist. To find critical points where derivative is 0, set derivative to 0 and solve this equation. This part, the left side is derivative. To solve this equation, factorization, then we see that 0 and 3 are the solutions. So the function has two critical points, 0 and 3. Okay, now to use this theorem, next, let's compute second derivative. Take derivative on the first derivative to get second derivative. Now, evaluate second derivative at the two critical points. At 0, plug in 0 in here, then I get 0. So 0, this critical point is in this case. First derivative at 0 is 0. Second derivative at 0 is 0. In this case, this theorem has no conclusion about the critical point. At 0, the function may have maximum, may have minimum, may have neither. At the critical point number 3, I plug in number 3 in x here. Then I get second derivative at 3 is 36, a positive number. Second derivative is positive. The curve is concave up. So at the point 3, the graph of the function f is concave up. So it is this case A. The function f has a local minimum at the point 3. So the minimum function value is negative 27. How to get negative 27? Plug in the number 3 in the function. Function value at 3, negative 27. It is a local minimum function value. Now, solution 2. Solution 2, I use this theorem to answer the question. Again, to find all the local extreme values, we first find critical points. Compute derivative, set derivative to 0, then we get two critical points, 0 and 3. Now, at the critical point 0, I want to know whether or not derivative changes sign at 0. On the left to 0, I pick a point, say negative 0.0, and evaluate derivative at negative 0.0. Derivative here. Plug in negative 0.1. Plug in negative 0.1 in x, then I get derivative at negative 0.1 less than 0. On the right to 0, I pick a point close to 0, say 0.1. Plug in 0.1 in the x here. Then again, derivative at 0.1 negative. Oh, this information says that derivative doesn't change sign at 0. On the left, negative. On the right, negative. So it is the case C here. So the function f has no local maximum, no local minimum at this critical point. So at 0, function has no maximum, no minimum. About the critical point 3. On the left, I pick a point, say 2.9. Derivative at 2.9 less than 0. On the right to 3, I pick 3.1. Arbitrary pick. Derivative at 3.1 positive. Therefore, derivative change sign from negative to positive at the point 3. It is case B. So the function has a local minimum at the point C. Yeah, the function it here means the function f has a local minimum at the point C. The local minimum function value at the point C, at the point 3, is negative 27. Second example under the topic number 3. Consider this function. Find all the local extreme values using the first derivative test. First derivative test means this test. First derivative. Go back to the example. To find all the local extreme values, first find all the critical points, because a local extreme value can only appear at a critical point. Now compute derivative on this function. This function is a quotient, so use quotient formula. Quotient formula to get this, to get the result. This is derivative of the function f. Derivative has a denominator. So when denominator is 0, derivative doesn't exist. Derivative doesn't exist when x is 1. When x is 1. However, 1 is not in the domain of the function f. The domain of the function of this function is any number except 1. Except 1. So here, any number except 1. I put an open dot here to mean excluding 1. Therefore, low critical points can make derivative doesn't exist. Now, to find the critical points where derivative is 0, we set derivative equal to 0 and solve this equation. Move the bottom to the right side, then we get this equation. Then factorization, and we have 0 and 2 solutions. Therefore, the function f has 2 critical points, 0 and 2. Consider 0 first. We want to know whether or not derivative changes sign at 0. On the left to 0, I pick, say, negative 0.5 and evaluate derivative at negative 0.5. Plug in negative 0.5 in x. Then I get this number greater than 0. Therefore, on the left to the critical point 0, derivative is positive. Similarly, pick a point on the right to 0, we get negative. So derivative change sign at the critical point 0 from positive to negative. So the function f, its graph is increasing on the left, then decreasing on the right, and therefore f has a local maximum value at 0. The local maximum function value is 0. Plug in 0 into the function. The function value is 0. Now, consider the second critical point. I want to know whether or not derivative changes sign at 2. On the left, I pick 1.5. This point is quite arbitrary to pick. Derivative at 1.5 is -3, less than 0. Derivative on the right side, I choose 2.5, greater than 0. So derivative changes sign at 2 from negative to positive. That means that the original function, its graph is decreasing, derivative less than 0, decreasing on the left, then increasing on the right of this point. So therefore, function f has a local minimum value at 2. The local minimum function value is 4. Plug in 2 into the function to get 4.